Hey, Corey here with the Mentored Engineer. So glad you could make it. I'm a little bit sad because I've worked all weekend through 3 specific problems that I've finally come up with solutions to, and I'm hoping to implement them this week. They all have to do with capacitor charging on our backyard roller coaster, Tilly's Terror. Yes, we are making progress on that. So the first issue I'm having is my capacitors, and I'm sure all capacitors over the face of the planet, don't charge evenly. So I have 40 capacitors in series, so one after the other. And if I put a voltage across them, they don't charge evenly. The first one may charge fully, the next one may charge half as much, and the next one might not charge at all. Spent a lot of time going through some documentation of figuring it out, and I'm like, the higher value I charge them, the more capacitors are charged at that higher value. If you want to think about it, it's like an ice cube tray if you're filling it now. This isn't an ice cube tray, but it's the best thing I have. So if I pour water in here and it dribbles onto the next one and the next one and the next one, this one will be full before the next one sees a drop. So that's kind of how it goes. So yeah, you can see that from the demonstration, I'm not going to get equal amounts of voltage in each capacitor, which is a problem for me, and it kind of leads to the second one. I was planning on measuring the voltage over 4 capacitors, thinking that all of them would have the same voltage. So if I'm charging to 96 volts and I took 1/10 of the capacitors, or 4 capacitors, and measured the voltage there, I'd get 9.6 volts, right? Well, that's not gonna happen. I've gotta measure the whole bank, which now is 96 volts, which brings up the next problem. My voltmeter only goes to 10 volts. 0 to 10 volts is what it'll read in safely. On top of that, it's gotta go all the way to the peak voltage, which I'm rectifying a 120 volt AC signal, so that's going to be 170 volts peak to peak. We get 170 volts because we take 120 divided by 1.414, and because that's the root mean square, so the peak will be 1.414 times that 170 volts. So I've actually got to be able to read 170 volts without my equipment going kapooey. All right, this stuff's really expensive. And that leads me to my third problem. So on my analog in and out card, they all have to have the same ground. So my analog outs use the common ground. One of my analog ins uses the common ground, and the capacitor one is going to use a different ground. Okay, so I'm pretty pissed. So how do we rectify this? So I could get an analog in card with 4 inputs. However, it's expensive. So the way that would go would, I'd have 1 voltage for the charge current, 1 for the lower value of the capacitors, and 1 for the upper value of the capacitors. And I could read all 3 of those in. I would subtract the 2 capacitor voltages, and that would happen in the PLC program, and then output that as my capacitor voltage. It could work, but those are it's like a $400 card with taxes, shipping, all that fun stuff. And I really don't want to spend that. So I took this opportunity to channel my inner Dr. Ferris from Baylor University. Back in, 1998, I took a circuits course with him. And I'm a mechanical engineer, so I don't really do circuits, but it was fun and I learned a lot of stuff. So one of the things we learned about was a voltage divider. And if you wanted to scale a voltage down, you could do that. You can't scale it up, I'm sorry. So what you would do is take 2 resistors and put them in a series, put one right on top of the other. On the top one, you'd put your input voltage. On the bottom, you'd put your ground voltage. In the middle, between the 2 resistors, you would take that, and that would be your signal. And depending on what your resistor value is how large or small that signal would be. So, if I have 2 1K ohm resistors, and I pulled off the center one, it would be half of the input voltage. So 10 volts in, I get 5 volts out. In my case, I want 170 volts in, and I would get 85 volts out. That's way higher than my 10 volt max. Okay, well, let's divide it by, let's just say 10. So in that case, I would put a 9K ohm resistor on the top and a 1K ohm resistor on the bottom. And the resistance, the voltage value would be the bottom resistor divided by the total resistance of the two. So 1 over 1 plus 9, and that would give me 1 over 10. Multiply that by 170, I get 17 volts. So while we could use two fixed resistors for our voltage divider, a much smarter way to do it is to add a multi-turn, in our case, 25-turn potentiometer. This allows us to get very fine metering of our signal, and we can just turn a screw and get it exactly where we want. 25 turns, that'll give us very good precision in this. Now I know that's over our 10 volt limit, and that's a very good question. I'm glad you asked that, but let's just hold on to that for a second. We'll stay with our 10-to-1 voltage divider. In that class, we also learned about operational amplifiers. Now those are cool things, and I actually had a practical application for them after I graduated from school, which, who does that, right? You learn something in college and then you use it? Whew. Anyway, so how this happened was I was in a band, I was a drummer. All right, so operational amplifiers, they allow you to do things with voltages. Remember how I said you couldn't scale up a voltage? Well, you can with an operational amplifier. If you set up an operational amplifier like this with these resistors, you can actually bring that voltage up to some extent. In my case, we had a microphone that just wasn't loud enough when we hooked it up to our practice amplifier, which we had for free. So we wanted to make it louder, and I took two 9-volt batteries, strung them together, took the voltage from the microphone in, and scaled it up by a factor of, I believe, 3, and then sent that out to the amplifier. And that was just enough to get it to, make it loud, and it worked. Rock on. So that's an operational amplifier. How they work, I really don't know, but you can do cool things with them. I already said multiply. You can add numbers, you can integrate, you can differentiate, you can make filters for these things. You can boost certain frequencies and minimize other frequencies. So one of the many things you can do is subtract voltages, and that's where we want to go. So what we're going to do is we're going to hook up our signal like this. We're going to put these 4 resistors in. We're also going to add our voltage dividers in. So an op amp is just a tiny integrated circuit. It has 8 pins on it because it's got 2 channels on this one. We're only going to use 1, but it only uses 5 pins. So you got to provide a power and a ground to this thing. Other than that, you just add in your 2 in voltages and your out voltage that goes to the PLC. So on our case, we have there's a negative terminal and a positive terminal. We want the positive terminal to the higher voltage and the negative terminal to the lower voltage. And we just add these other resistors in there. Now first we're going to put our potentiometers that are our voltage divider, and then we'll have these 4 resistors. So 2 different schematics, don't get them confused. So using the subtracting op amp, it allows me to get those 2 inputs down to 1, and it'll be in that 0 to 10 volts because my capacitors will only charge up to 96 volts before I shut them off. So, hey, it's a win-win-win-win-win, right? Nice. It's great that I was able to solve all these problems. So what I'm going to do is make this little tiny board right here. This will be our op amp with the voltage dividers and the resistors. And we're going to put it in this box here so we protect it from stray electrical wires. And we're also going to add these 2 0 to 10 volt in to PWM outs. And this chip right here is what drives our PWM signal to our transistors to get the capacitors to charge and the motor to move. So let's now go to our test bench and we'll see how this plays out. We are here at our board. I've made this board right here. Here's a closer shot of it. That has the voltage dividers and the op amp to subtract the 2 voltages. And then I put this board right here to give me a visual indicator if the board is charged at all. It's not the highest quality. We'll get to that in a second. All right, so let's go ahead and charge this. That's enabling. And here we go, charge. You can see the current spiked up right there to about, it says 6 amps, but I haven't calibrated it yet. And the voltage is climbing. It's at 1.7 volts, almost 2 volts right there. And you'll notice here, this should be reading 0.2 volts, but it's not. And that's where the, if I go ahead and put my voltmeter here, we'll set that right there, and we'll go ahead and read it. Look at this, I got 0.394 volts, and I'm getting 0.1 there, so it's off by a bunch. So, what do you expect? This Amazon for like 12 or 13 bucks. I do have another one, so I'll swap that out and see if that makes any difference. You can actually see it spiked up right there, so maybe it's just out of its normal range. It's such a low spot of a 0 to 100 volt thing that maybe it's not that accurate. Especially since I'm only feeding in at 0.5 volts. The other thing I could do is take the actual two voltages of the high and low and run it through there and see what happens. All right, you can see here my current's still high, my voltage is climbing, so it's doing what it's supposed to. Now I just got to add in some cutoffs and some safety protocols in there. No big deal. Hey, so thank you for watching The Mentored Engineer. I'm Corey. Please take a second to like, share, and subscribe. It helps. Hey, click that join button too. Get involved. Thank you. And have a wonderful afternoon or morning. I don't actually know what time you're watching this, so it could be any time. Anyway, thank you.